Okay, here, 8.7, number 3, the instructions for the given integral have two parts, one for the trapezoidal rule, one for the Simpsons rule. Complete the following parts. So we're given this integral. First thing, using the trapezoidal rule, complete the following steps. Estimate the integral with n equals 4 steps and find an upper bound. And there's 9 parts to this one, so we'll go through this one kind of quick. Let's do this one in Word, just because the formulas are so obnoxiously long. All right, so the trapezoidal rule. There is a formula to that sum t is that delta, what is it, delta x, I think, over 2, and then y naught plus 2y1 plus all the way down 2y sub n minus 1 plus just y sub n. All right, so make sure you have that formula in front of you when you go to take the test. I'm almost certain this formula is on the formula sheet. All right, so we're given n is 4, and we are going between negative pi over 2 and positive pi over 2. That is a total distance of pi, which means that each of my step sizes is going to be pi over 4. Okay, so that's going to be my delta x. Delta x is just going to be pi over 4. So we're going to take that and divide that by 2, and that's going to be times. My function is the 4 cosine t, and we're starting at negative pi over 2, and we're going to keep adding pi over 4 until we get to positive pi over 2. So the first thing we're going to do is we're going to plug negative pi over 2 into the function. So 4 times cosine of negative pi over 2, we'll get to that in a second. That's going to be plus 2 times plugging the next value over. So adding pi over 4 to this is going to be negative pi over 4. So 4 cosine of negative pi over 4. Plus 2 times the next one would be 0. So 4 cosine of 0. Plus 2 times the next one would be 4 cosine of just regular pi over 4. Plus the last one would just be 4 cosine of pi over 2. Okay, you could either look at a unit circle to figure out all these values are. You could probably get away with typing this all into the calculator because it is asking just for the rounded answer to 4 decimal places. And I don't have my calculator with me, so I'm going to need some help here. So just make sure you're in radians and type all that in, and let's see if we can get an actual answer. I don't know where my calculator went. I had it. Oh, I think I left it downstairs. You guys type that in. I'm going to go grab my calculator. How to get a calculator? Okay, so let's see what all this is. All right, I'm almost certain, and I might have typed it in wrong because I skipped some steps here. This came out to be 5.6407. So, I don't know, let's see if that's right. Nope, I typed it in wrong. Or maybe I'm not in the right mode. Let me just look back over to make sure I typed it in all right. Oh, I have the calculator on the screen. I could have just used that. The pi over 2's are both just 0. We can ignore those. And then 8 cosine negative pi over 4 plus just 8 plus 8 cosine pi over 4. I think I typed it in right. Let's try this calculator. All right, so it was pi over 4. That divided by 2 times 8. No, not 8. Oh yeah, because that first one's 0, right? So 8 cosine of negative pi over 4. Okay, that plus 8 cosine of 0 is just 8, plus 8 cosine of positive pi over 4. And then the last one's also 0. Now I got something different this time. 7.5845. 7.5845. There we go. All right, I must have typed in something funny on my calculator here. Okay, so that was part 1. Let's keep going. The next thing it's asking us to find is the upper bound for the error, and there's a formula for this one as well. So the error formula for the trapezoidal rule, and this is just something that you'd have to look up, it's less than or equal to a fraction. It's m times b minus a, I think to the third, divided by 12n squared. So that's off of memory. I might be wrong on that. So for us, it's going to be less than or equal to. Okay, the m is the upper bound of the second derivative between negative pi over 2 and positive pi over 2. The second derivative of 4 cosine t would just be negative 4 cosine t. So we want to think about the graph of negative 4 cosine t between negative pi over 2 and positive pi over 2. But it's not just that it's the negative value, it's like the absolute value of that. So let me go into Desmos here and we'll just graph it. All right, so this is the second derivative that we're graphing, and we want to find the maximum. So negative 4 cosine of x. Great. And remember, we're in between negative pi over 2 and positive pi over 2. In between these two values, here and here, the maximum value is negative 4, but you take the absolute value of that. So the furthest distance from 0 the second derivative takes is a positive 4. So we're going to plug a 4 in for that m. That's going to be times b minus a. B minus a is negative pi over 2 minus pi over 2, so that's just going to be pi cubed divided by 12 times the n. Remember that n was pi over 4. Oh no, sorry, not pi over 4. That's the step size. Our n is just 4 squared. All right, so that we'd want to type into a calculator. Again, it wants 4 decimal places. It's hard to get everything on the same screen with my limited space here. So that 4 pi cubed, that divided by 12 times 4 squared, which is 16. So we get this, 0.64596, so 0.6460. Cool. Okay, so is that part all right? I know I'm jumping around to a bunch of different screens here, but this is just plugging stuff into the formula. Is finding the trapezoid sum and finding the maximum error okay? Requesting to annotate the shared content. I knew you were trouble, Lauren, from the beginning. Let's see what you do. Can you draw my screen now? Because that would be weird. Any questions about this stuff so far? Is that all right? Because there's 7 more parts to this question. Okay, great. So just to keep it going, evaluate the integral. So that's just going to be doing the integral. I hope everybody's okay with that part. Oh, can everybody else hear me? That would have been bad. It would be even worse for you guys to not be able to hear me and not tell me. Everybody can hear me, right? Okay, great. I don't know, Lauren. It must be something... Must be on your end. We'll keep going. All right, so just to do this integral here, so that'll be the integral from that negative pi over 2 to positive pi over 2. We'd want to find the antiderivative for this 4 cosine t dt. Pretty easy to find. So the antiderivative there is going to be positive 4 sine t. And then we're just going to evaluate this between pi over 2 and negative pi over 2. If I plug pi over 2 into this, I'm just going to get 4 minus, if I plug negative pi over 2 into that, I'm going to get negative 4. So those two things are going to add together to be 8. Great. So you can see like how good of a job this trapezoidal rule does, because the approximation came out to be 7.58. The actual answer came out to be 8, and that was with only a step size of 4. Of course, when you do this kind of stuff in the calculator, it does a lot more step sizes than that. So now it's asking for what is the actual error. To get the actual error, you're going to take the actual value 8 and then subtract away the approximation. So just 8 minus 7.5845. We get 0.411, or what was it? 0.4155. Okay. So this number up top was the maximum possible error for doing it with 4 step sizes. This is what actually happened when we did it. So this number is always going to be bigger. And then it's asking us to find the percentage. And it gives you the formula for that, but it's nothing too crazy. So just take this thing that we just got, this 0.4155, and then divide that by the true value, which was 8, and then just change that into a percentage. So 0.4155 as it is divided by 8. That change to a percentage would be what, 5 point, what do they want? 1 decimal point, so 5.2%. All right, and then it wants us to do the same exact stuff, but this time for Simpson's rule instead. So everything is the same. The only difference is now it's a different formula. So for Simpson's rule, it is that delta x, but this time it's that delta x over 3 times the first y value plus 4 times the next one, plus 2 times the next one, plus all the way down 4 from the second to last one. No, sorry, 2. 2 times the second to last one, plus 4 times the next to last one, and then plus just the last one. All right, so I know that formula is kind of awful looking the way it's written up, but it's just that the algorithm for it. So plugging stuff into what we had, because everything's the same, the delta x is still pi over 4, and then these y values are all still the same. So that's going to be that pi over 4, but this time divided by 3, times the first y value, remember that was just 0, plus 4 times the next one, which was 4 cosine of that negative pi over 4. This was supposed to be negative. Plus 2 times the next y value, which was 4 cosine of 0, plus 4 times the next one, which was that 4 cosine of positive pi over 4, and then plus just the last one. The last one was also 0, I think it came out to be. All right, so this is what we would type into the calculator this time. So the pi over 4 divided by 3 times, so 4 times 4 is 16 cosine of negative pi over 4. That plus 4 times 2 is 8, cosine of 0 is 1, plus 16 cosine of regular pi over 4. All right, so 8.0182 it looks like. That looks about right, because remember it's supposed to be close to 8. 8.0182, is that what he said? Yes. All right, so just plugging stuff in from the formula. Okay. This is probably the hardest part of the whole thing, is finding the upper bounds for those errors. The formula for the Simpson error is still less than or equal to m, but now it's b minus a to the 5th divided by 180 into the 4th. Again, that's off memory, so I may be a little bit off there. Where this equation is coming from is above our pay grade. So don't worry about that. Just know that this is the formula to use when finding the maximum possible error using either trapezoid or in this case Simpson's. This time the m is different though. The m does not represent the maximum value of the second derivative. This time the m represents the maximum value of the fourth derivative. The fourth derivative of 4 cosine t is just 4 cosine t, which means that the maximum value is still going to be 4. So 4 pi to the fifth, again b minus a is that pi, divided by 180 times 4 to the fourth. All right, so we'll type that into the calculator, 4 decimal places again. All right, so that 4 pi to the fifth, that divided by the 180 times 4 to the fourth. I got 0.026, this is 4 decimal places, 0.0266. Cool. Okay, and then I imagine the rest are the same. Evaluate the integral directly. We already did that up top. That was still 8. That hasn't changed. Find the actual error. This would be taking 8 minus this. It is absolute value, which means we'd have to change the negative to make it positive. This would just be the decimal up there, that 0.0182. And then define the error percentage. So taking that 0.0182, dividing that by the actual value 8, changing this to a percentage, this time it comes out to just be 0.2%. Just move the decimal over twice. All right, I finished that one up very quick, but that's because we already took 15 minutes doing this. Oh yeah, the question, Richard. Sorry, I didn't see that. What's your question? Was it from above?
Yeah, it was from the initial m value. So the m value, that's where I skipped. You did the cosine pi over 2 and the cosine negative pi over 2, so that's why it became cosine pi. So
yeah, the pi is because this total distance here between negative pi over 2 and pi over 2 is pi. So that's where that pi is coming from.
Okay.
So you take that and then you divide that by the step size to get the pi over 4.
Okay. All right.
Does that make sense?
Yeah.
Okay, cool. Anything else? Any other questions about number 3 here on 8.7? Is there any other homework questions you want to look at? From either 8.7 or 8.8? 8.8, number 5. Yeah, let's look at that one. All this stuff. Okay. So for this one, let's go over to OneNote here. Let me just copy it down. So we have the integral from 0 to 2, I don't like theta, so I'm going to put x's. 2x plus 13 over the square root of x squared plus 13x dx. Okay. So first off, when it comes to the test, you're going to have to be very careful about questions like this. Do not just automatically start doing the question. You always need to ask yourself if there are going to be any holes or asymptotes, and we are going to have one here. So the domain for this question is that we are not allowed to plug 0 into it. So x cannot be 0 because that makes the denominator to be 0. Everything else should be fine because everything between 0 and 2 are all positive numbers, and plugging positive numbers inside of a square root is okay. So what we have is that one of the endpoints for my integral creates an asymptote. We can still do the integral, we just have to be more careful about it. We're going to write it like this, right? We're going to do the limit as a approaches 0. Now you have to be careful about which direction it approaches. In this case, it's approaching it from the right. It's approaching it from the right because if I'm going between 0 and 2, I'm closing in on the 0 from the positive direction, so I'm approaching it from the right there. Okay, that, and then all we do is we just substitute out the 0 with an a. So now it's the integral from a to 2 of the same thing, 2x plus 13 over square root x squared plus 13x. Okay, now we do the integral the same way that we would from earlier in chapter 8. In fact, this is going to be one from Calc 1 because this is just going to be a regular u substitution. If you look, if I make u be the inside of the square root, that x squared plus 13x, if I take the derivative of that, I get the numerator 2x plus 13. So that means that 2x plus 13 dx is going to substitute out to be my du. Now my integral is going to be still the limit as a approaches 0 from the right. Because I'm doing a u substitution, my limits have now changed. The 2x plus 13 dx is now du. In the denominator, that's just going to be the square root of u. Okay. You can think about this as being that same limit, blah, 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 blah. This time the integral u to the negative 1/2 du. I like looking at these as being fraction exponents instead of square root exponents. Just it's easier for me to do it in my head. So now the antiderivative here, that negative 1/2 is going to raise up to positive 1/2, and then we'll divide. So we're going to have a 2 out in front, and then that's u to the positive 1/2. Okay, plugging back in the substitution, that's 2 x squared plus 13x to the 1/2. This we're evaluating between a and 2, and I forgot my limit thing, but that limit thing's still supposed to be in front of all of this. Now we plug in our limits. So when I plug 2 into this, two squared is 4, plus 2 times 13 is what, 26? So 4 plus 26 is 30, and then the square root of 30. So 2 square root 30. That's going to be minus plugging a into this, and there's not really much we can do except just substitute the x's for a's. All right, now that we have this, again, we want to go back to Calc 1 stuff, and we want to think about how do we plug in this limit. One good rule of thumb is that if you can plug in the number and it works out, then just plug in the number. If I do replace these a's with zeros, everything will be fine, because this will just be 0, plus this will be 0. 0 to the 1/2 is still just 0, so this whole thing just goes away. In other words, my final answer is just that 2 square root 30. And maybe that can be simplified down. I don't think so, though. So just 2 square root 30 should be our final answer here. Okay, so was that one all right? Is there any questions about that one? So this is doing the integrals whenever you have an asymptote as one of the endpoints. You have to do this limit trick. Any other questions from the homeworks? Okay, so if there's no more questions from the homeworks, then what I want to do for just a little bit is let's look through this. I don't even want to call it a worksheet. It's embarrassing to call it that, but let's work through this practice stuff thing. So what I did on this is I just put a bunch of different practice integrals of the stuff that you guys are going to have to be able to do on the test coming up this week. A couple of word problems at the bottom with the trapezoid rule and the Simpsons rule stuff. So let's just start at the beginning and let's look through each of these and kind of talk our way through them. Okay, so this first one here, integral x squared sine of 1 minus x. You need to be able to look at an integral like that and know right away which technique you're going to do to be able to solve this. So you'd start at section 1. You'd look at the integration table to see if it looks like anything on there. U substitution would probably be the main thing to try, although that's not going to work for this question. And then there's a bunch of different other techniques we saw for section 1, but none of them really dealt with questions like this. After that, we did integration by parts. Integration by parts is when you have two functions multiplied together where one of them would break down with derivatives. And that's exactly what we have here. We have the x squared and then the sine of 1 minus x multiplied together. If I let u be the x squared, eventually it's going to break down to be 0. All right, so integration by parts with this one. When you're doing integration by parts, you have to have this formula, the uv minus integral v du. Either have that memorized or have it written down somewhere. With integration by parts, you need to set your function u and you need to set your function dv. So like I said, we're going to let u just be the x squared because I know that one breaks down. We'll let the dv be the sine 1 minus x dx, just everything else in the integral. Make sure that's something that you at least know how to find the antiderivative. So once you have the u and the dv, you want to find your du, which is just the differential of u. And then the dv, you want to find the antiderivative for. This is be a little bit careful with this because of all the signs floating around. The antiderivative of sine is negative cosine, but then we're going to take out the negative 1 that's multiplied on the x anyway. So this comes out to be positive cosine 1 minus x. You can always double check to make sure you did it right by taking the derivative of v and making sure it comes back out to be dv. All right, now that we have this, we're going to plug that into my formula up here. So u times v, this comes out to be x squared cosine 1 minus x. And that's going to be minus the integral of v cosine 1 minus x times du, which is 2x dx. But I'm going to put that 2x in front, the dx in the back, just because that's how I like to write them. Okay. Unfortunately, we're left with another integral that we're going to have to do another integration by parts. And this is very common and something that you're going to have to do a lot. If you want to, you could pull the 2 out of there. In fact, I'll go ahead and do that, which means that my u is just going to be x, and then the dv is going to be that cosine 1 minus x dx. So now u has differential du, which is just 1 dx. V, which is the antiderivative of cosine 1 minus x, this time it's going to be negative sine 1 minus x. And make sure that makes sense to you. Now we do that formula again. So just copying down where we left off, we still have the x squared, we still have the cosine 1 minus x. Remember that I pulled a 2 out of this integral, so now it's a negative 2 times this integral that's left over, the x cosine 1 minus x, is going to be another integration by parts. So u times v, which will be negative x sine 1 minus x, minus the integral of v, negative sine 1 minus x du, which is dx. Okay, and now we just clean this up. So we still have this x squared cosine 1 minus x out in front. This negative 2 is going to distribute onto here to make this a positive 2x sine 1 minus x. These two negatives are going to cancel each other out to be positive. And then the antiderivative of sine of 1 minus x is positive sine of 1 minus x. And then don't forget your plus c. And then we're done. So we have x squared cosine 1 minus x plus 2x sine 1 minus x plus sine 1 minus x plus c. All right, so integration by parts. Do we all feel 100% about integration by parts, even if you have to do it multiple times? Cool. All right, looking at the next one here, b. So e to the x cosine. Oh, what's that? Scroll to the bottom? Yeah. There you go. You're welcome. So this next one here, b e to the x cosine 2x, this is still going to be integration by parts, but this is one of those integration by parts that eventually you're going to have to wrap it back around to the beginning. Does anybody want to see this one, or do we feel okay about integration by parts, even these more complicated ones? Okay, I'm going to go with everybody's good. Okay, let's look at C then. So C, integral x plus 1 over x squared x minus 1. So let's go to a fresh page here. It was integral x plus 1 over x squared times x minus 1 dx. Okay. Again, running through all the different things that we have. This is a fraction. Sometimes long division works, but long division will only work whenever the numerator's degree is the same or bigger than the denominator. My numerator has a degree of 1. My denominator ends up having a degree of 3 when you multiply it all out. So definitely not that. You can't split up this fraction just as is. I mean, I guess you could put the x over the bottom plus the 1 over the bottom, but that's definitely not going to help out. This also does not match anything on the integration table, and we do not have like squareds that are added together or subtracted, so it's not going to be the trig substitution stuff. What I'm noticing with this question is that the denominator is completely factored, and then the numerator has a smaller degree, which means that we're going to be doing partial fraction stuff. So what I'm going to do is I'm going to go over to scratch paper, and we want to find the partial fraction decomposition of x plus 1 over x squared times x minus 1. We have two linear factors, x and x minus 1. My linear factor x is squared though, which means that I'm going to get a constant over the x squared plus a constant over the x plus a constant over the last factor x minus 1. All right, remember that whenever you have a power on the factor, you're going to have a fraction for every single one of those powers going down to 1. Linear factors always get constants up top. Now we want to find the a, the b, and the c. We're going to do that by multiplying this denominator onto both sides of my equation. When you multiply it on the left-hand side, everything cancels except for that x plus 1. When you multiply it on the right-hand side by this first fraction, the x squareds cancel. We get the a coming down, and we get the x minus 1 factor. Plus, the b comes down. One of the x's cancel, so we still have the other x, and then we have the factor x minus 1. Plus c, the x squared comes down, and then the x minus 1's cancel. All right, At this point, you can find the a, the b, and the c however you feel comfortable doing that. If you like doing the method with the coefficients of the different power functions, then do it that way. If you like just plugging in x values, then do it that way. It really doesn't matter. Sometimes one is easier than the other. I think the last time we did one of these together, I did the coefficients thing. So this time, let's do one where we're just plugging in numbers. You want to try to plug in x values that make stuff disappear. If I plug in 1, it's going to make these two parentheses just go to 0, so they're both just going to go away. So if I plug 1 in for the x's, I'm going to get 1 plus 1 on the left-hand side, so 2. This is 0, plus this next one is 0, plus plugging 1 into here, I'm just going to get c. So this automatically tells me that c is 2. All right, from there, let's plug in different x values. Another x value that would make stuff disappear is going to be 0. That's going to make the b and the c disappear. If I plug 0 into the left, I'm going to get 1. If I plug 0 into the right, I'm going to get negative a. This tells me a has to be negative 1. The last thing I'm missing is the b, and I've kind of run out of numbers to try to make stuff disappear. So I'm just going to plug in maybe 2 and see what happens. If I plug 2 into the left, I get 2 plus 1, which is 3. Then I'm going to have the a, remember the a was negative 1, times 2 minus 1, which is 1, plus the b, I don't know what that is yet, times 2, times 2 minus 1, plus the c was 2, times the x2, so 2 times 2, 4. Simplifying all this down, we get 3, we get a negative 1 there, plus 2b plus 4. That comes out to be 3, and if I subtract that over, I get 0 is equal to 2b, which means that b has to be 0, which is fine. Okay. What all this tells me is that now that I have my a, my b, and my c, I can plug them back into this. A over x squared plus b over x plus c over x minus 1. So that fraction we started off with, x plus 1 over x squared times x minus 1, will break down into a, which was negative 1 over x squared, plus b, which is just 0, so that whole term is 0, plus c, which was 2 over x minus 1. Okay, instead of integrating over this left-hand side, we're going to do two separate integrals over the right-hand side. This first one, the negative 1 comes down, and then this is x to the negative 2. Dividing that is going to be, increasing the negative 2 to negative 1, and then dividing is going to cancel out the negative. So we're just going to get a positive 1 over x there. Plus here, we're going to pull out the 2, and then the antiderivative will be natural log x minus 1 plus c. And then that's it. That's going to be our answer for that one. Again, I know I went through that one kind of quick, but that's just partial fraction stuff. Is everybody okay with that one? Is there any questions about that one? Okay, cool. So I'm going to skip D. D is really something kind of similar. It's a little bit different because an x will just cancel out from top and bottom. I guess we should do. All right, let's just do this one real quick. So integral 4x over x cubed plus 4x. All right, be careful with your algebra rules here. The 4x's would definitely not just cancel out top and bottom. That's not how it works because of this plus sign downstairs. But what we can do is we can factor an x out of the denominator. And then I have an x up top and an x on the bottom that cancels out. So now we're left with this integral of 4 over x squared plus 4 dx. We can pull that 4 out because that's not really doing anything. And we're left with this, the integral of 1 over x squared plus 4. At this point, this integral that we're left over with here I hope that this starts looking familiar. This is one of the integrals that is on that integration table. I think the antiderivative for this one is tangent inverse. So this is just off memory. You have the 4 out in front, and then it's 1 over 2 tangent inverse of x over 2. I don't know if that's right. That was off memory. I just didn't feel like pulling up the integration table. So anyway, it's from the table. Everybody okay with that one? Any questions? Nice. Okay, now let's look at the last one here. Or not the last one, sorry. What are we on? We're on E. So the integral t over square root 4t squared minus 1 dt. Okay, again, go through all of your rules. This one is just going to be a regular u substitution. I know in that denominator it's two things that are squared and subtracted, which means that you could actually do the trig substitution stuff with those triangles and the angles, but there's no point. We can just set u to be the 4t squared minus 1, and then du would be 8t dt. Now I know that 8 is kind of pesky, but we can divide that over. The t dt is going to become 1/8 du, and then my denominator is just going to be the square root of u. So the 1/8 comes out. This is u to the negative 1/2. That negative 1/2 is going to go to positive 1/2, and then you're going to divide to be 2 plus c. And then just don't forget to plug back in the u. 1/8 times 2 is 1/4. U was that 4t squared minus 1. That's all to the 1/2 power plus c. All right. The point of that one is, I know we've talked about a lot of techniques here in chapter 8, but don't forget about u substitution. A lot of times u substitution can be used. Is that one all right? Questions about that one? I love the names that they get for these OneNote things. I don't know. Set it east, dust it. Somehow it got that out of what I just wrote up here. That's amazing. Okay, let's do one more. This next one's pretty difficult, so we'll look at this one and then we'll probably get out of here for the day. So this last integral f, and we'll do the rest next time. Integral dx over x times 9 minus x squared. Okay, going through the motions again. U substitution would probably be what you want to try first. But if you let u be the inside, the x is in the denominator here, which means it's not going to substitute out with the du. After that, maybe partial fractions would work, because this 9 minus x squared, that would factor out. This is a difference of squares. So you could do 3 minus x and then 3 plus x, and then you have 3 linear factors to do the different fractions. You could probably do it that way, and it would work out just fine. Another thing that you could do with this one is that you do have the squares, 9 minus x squared, which means that you could do one of those trig substitutions as well. Both of those would probably work, and both of those would give significantly different answers. But not different. All right, so different was the wrong word there. They would look different, but they would be exactly the same. If I had this question, I would probably do the trig substitution stuff. So first thing we want to do is decide which substitution to do. Here we have the constant in front minus the x squared. If you are looking at the right triangle, that means that this square root 9 minus x squared, oops, not there, would have to be one of the sides. I'm not exactly sure which side we should label it as. Let's just put it here for now. So the square root 9 minus x squared. Because the 9 is in front, that means that's the bigger of the value. So the square root of that has to be the hypotenuse, which means that this has to be the other leg. If I let my angle be here, that would be cosine of theta is x over 3. But we don't ever do cosines, right? So let's not put the angle there. Let's put the angle up top. That way I would do sine of theta is the opposite x over 3. And if I multiply the 3 over, that gives me x is 3 sine theta. 3 sine theta was one of the ones that we had as our examples. All right, so this is the substitution I'm going to do for this one. Not only do we have this, but we also have to find the differential. If x is 3 sine theta, then dx is the derivative of that, which is 3 cosine theta d theta. And it would also be nice to figure out what 9 minus x squared is, the thing inside the parentheses down there. 9 minus x squared would be 9 minus 9 cosine squared, which would end up being 9 sine squared. All right, now let's plug all that in and see if it looks good. Just looking at it, it's kind of looking bad. My dx up top, that's 3 cosine theta d theta. The x, that's the 3 sine theta. And then that parentheses, that 9 minus x squared, that's going to be 9 sine squared. All right, so that was just substituting all this stuff in that we've made over here in our substitution box. Let's see if this is anywhere manageable. So these 3's cancel. I'm going to pull that 1/9 out just so we don't have to deal with the fractions. Then we have cosine theta over sine theta. And then we have 1 over sine squared. I'm not really sure how to write that out. Cosine over sine, that's cotangent. 1 over sine squared, that's going to be cosecant squared. That's not really anything, is it? Oh, I know what we should do. All right, scratch that. Don't do that. Pulling the 1/9 out, let's leave this as cosine theta over sine cubed. Then we'll just do a u substitution. We'll let u be sine theta, and then du would be the differential of that, cosine theta d theta. That way the cosine theta d theta becomes the du. And I'm just going to end up with 1 over u cubed du. This has antiderivative, so that -3 would go to a -2, and we would divide by that. So -1/18 u to the -2 plus c. And then plug back in the u, which was sine. Okay, again, I know I went through that one like kind of quick, mainly because I don't know if I'm boring you guys to death. But there we go. So that was the way to do that one with the trig substitution. You could have done this other ways, like I said, with the partial fraction stuff. Is that one all right? I feel like that one was kind of sloppy compared to the other ones. Is there any questions about how I went through that one? That's on the test? Yeah. So these trig substitutions here with these triangles is going to be on the test. That's the stuff from section 5. I will say that section 5 is probably the most difficult section that you'll see in the entire Calc 2. This stuff with these trig substitutions. I didn't even really finish it, right? Because remember, you're not supposed to have thetas as your final answer. I should have switched this back over to x's. We could do that because x is just 3 sine theta, So this 18 sine squared would substitute back out to be, what would it be if I took 2 6s out of there? Or no, sorry, 2 3s out of there. So just 2x squared plus c. These are the same thing. Yeah, so don't forget to do that. If your original question is in x's, make sure you have x's in your final answer. Don't leave them in terms of theta. Substitute them back out. Okay, great. So there's still a lot of questions here that we did not get to on this practice stuff Word document that I have. We have time on Thursday, if you can make it to that, to do those. As always, I recorded this, so if you weren't able to follow some of the stuff we did, I'll put the recording up in Moodle and you can kind of go back through it. After the Chapter 8 stuff and when you're done with the test, I have started making the Chapter 9 videos. Chapter 9 is going to be a very small chapter, and we're not going to be having its own test on Chapter 9. But the Chapter 9 material will show up on the final exam, so just make sure you kind of take it seriously. All right, any last questions before we get out of here for the night? Okay, great. Well, let's go. Thanks for coming tonight. Hopefully I'll see everybody on Thursday at 1 p.m. And if I don't see you then, good luck on the test.